Hello. Today I'd like to share with you work that we've been conducting regarding the use of automated lab reactors such as METTLER Toledo's EasyMax and OptiMax coupled to process analytical technology or PAT such as FTIR spectroscopy in order to inform rapid decision making for a key clinical program moving through our development pipeline. Before getting into the details of that particular process, I wanted to highlight a little bit about how automated lab reactors fit into typical workflows within our department, chemical process development and commercialization. Specifically wanted to focus on how those tools are seeing routine usage within our technology laboratories. And I wanted to give an overview of how our department actually manages technology development and new technology deployment within our organization. I specifically sit within chemical process development and commercialization at Merck, which is essentially a small molecule API design and development organization comprised predominantly of engineers, about 70 or so engineers with a few chemists. Within CPDC, our functional area, we also maintain a set of dedicated technology laboratories, and those particular laboratories are tasked with developing new and emerging technologies around a unique set of core and enabling technologies and are staffed with subject matter experts in each of those particular areas. The 4 technology labs within our organization are the crystallization laboratory, the particle engineering laboratory, the reaction and separations laboratory, and the group that I lead, which is the process development intensification laboratory, or iLab. In addition to new technology development, each of these labs is responsible for providing direct project support as well, particularly in instances where either the runway is very short for a particular deliverable or where there is extreme technical complexity of a particular process. Specifically thinking about the intensification laboratory, the iLab, our core mission within the process development intensification lab is to enable the acquisition of deep, robust process understanding, but doing so in a resource-sparing way. Here I refer to resources not just from a cost perspective, but also from a time and an FTE deployment perspective as well. So really kind of focusing on how can we build mechanistic insight as efficiently as possible. I would say that our mission is kind of centrally focused around the concept of data intensification, meaning how do we go about collecting data more efficiently? How do we take that data and reduce it into manageable pieces? And then how do we perform data analysis that can be used to then drive either process design or business-based decisions? This is all facilitated through the judicious choice of enabling technologies such as process modeling, high-throughput automation, process analytical technologies, automated reactor implementation, statistical design experiments, etc. From an equipment capability perspective, the iLab, much like most of the technology labs and even many of the project labs within CPDC, are outfitted in what we consider to be a pretty typical but relatively modern reactor configuration. So we have a number of hoods that are dedicated to automated lab reactors, such as the one shown here that has both, for example, an EasyMax vessel and an OptiMax vessel, allowing seamless transition from the 100 ml scale up to the 1 liter scale. It's also fully instrumented with METTLER Toledo's PAT technologies, so PVM, infrared spectroscopy, FTIR, FBRM, and we also have capabilities from a Raman perspective as well. In addition to the PAT technologies that I described on the last screen, I also wanted to highlight some of the other capabilities that we have within the iLab and then the rest of the tech labs for that matter within CPDC. So there's an assortment of automated reactors that include the EasyMax and OptiMax as I showed, but also including things such as the Multimax and the RC1. We also have access to a number of benchtop automation type systems that are more high throughput or parallel operation equipment. So Integrity 10 parallel reaction blocks, as well as its associated AmigoChem parallel sampling technology. We also have a HEL polyblock capabilities, as well as are actively evaluating the ChemSpeed auto plant for parallel reaction execution. We also have METTLER TOLEDO's Easy Sampler that we use to do product monitoring via automated HPLC sampling. We find that to be a really informative piece of equipment as well. From a process modeling perspective, we have a number of home-built process models, but we also leverage some commercial packages like DynoChem, Aspen, Fluent, and G-Crystal for various types of modeling activities. In addition to these capabilities, we have a substantial array of analytical capabilities at our disposal. That includes particle characterization and other typical analytical tools. And when looking holistically at all of these capabilities, it forms a suite of tools that lend itself to modern experimentation strategies and robust process understanding builds. Again, taking a look at Inline PAT, as I mentioned previously, we have a number of METTLER Toledo based PAT technologies. So FTIR for reaction solute concentration monitoring. We have Raman spectroscopy that we use predominantly for polymorphic form transition monitoring. FBRM for crystal size monitoring in situ or chord length distribution specifically, as well as in situ microscopy in the form of PVM. So in addition to those PAT technologies, as I mentioned, we are heavily invested within METTLER's ecosystem for automated lab reactors as well. That includes both the EasyMax and the OptiMax automated lab reactors, amongst others. Most of the discussion that I'm going to talk about today is a summary of experiments conducted at both the EasyMax and the OptiMax scale. To give a little bit of an overview on the EasyMax, it's a dual reactor setup. It has vessels that range from 10 to 100 milliliters in usable reaction volume. It's an automated system in the sense that it has precise control and real-time monitoring of key reactor data, which includes things such as temperature, agitation rate, reagent dosing volumes, etc. It's also very well integrated into the iControl suite of software, which allows for pretty convenient data sharing across multiple platforms, such as FBRM, FTIR, PVM, etc. It also has the capability to interface with METTLER's universal control box, which allows us to bring in analog signals from other third-party vendors, enabling us to keep a pretty robust data set, all self-contained within the iControl suite of software. So in that regard, it's actually incredibly attractive. Additionally, we also have a number of OptiMax vessels, which personally I consider to simply be a larger sibling of the EasyMax, vessels ranging in volume from the 250 ml scale up to a liter scale. I would say it has pretty comparable automation capabilities to the EasyMax. One of the benefits of this is that it allows pretty seamless transfer of a recipe for a particular process as you move from a 100 ml scale up to the 1 liter scale. So by now I hope that you have a little bit of an understanding around some of the capabilities that we have within the technology labs and more broadly within CPDC here at Merck. I wanted to just take a really quick minute to just touch on the concept of just kind of targeted development, right? So one place where the tech lab resources provide significant business benefit, as I mentioned earlier, is on data collection and interpretation on a very short timelines. When you have a very abbreviated timeline where before a deliverable needs to be met, sometimes you have to make business and process design based decisions with pretty limited data sets. So one of the places where the tech labs add value is by leveraging both technological tools as well as deep scientific and subject matter expertise. We're able to build process understanding as rapidly as possible and then make informed decisions on those short timelines. For the remainder of today's discussion, I'm going to focus on rapid data collection interpretation for a particular project to support risk assessment and mitigation activities as a program was moving from the lab scale up to a pilot scale reaction system. This happens to be to support a key phase 2B clinical delivery. It turns out to be the first clinical delivery from our pilot scale facility. So we wanted to make sure that we were understanding the process sufficiently so we could make intelligent equipment and process design decisions in order to maximize the probability of success for this particular process. This particular synthetic scheme is one of the two chemistries that we're going to be focusing on today. And it highlights the application of these tools in identifying and mitigating risk, moving from lab to pilot scale execution. So the synthetic scheme that I'm showing you here is a palladium catalyzed CO coupling. It actually takes this aryl chloride here and it couples it to this primary alcohol. Again, it uses palladium acetate as well as Brett-Phos, which is the ligand for this particular system. And it forms this aryl ether here as the product of the synthesis. One thing to note is that this particular chemistry is mediated by the inorganic base, cesium carbonate. That actually has a number of significant implications that we're going to discuss over the next few slides, specifically stemming from the fact that cesium carbonate has virtually no solubility within the solvent system toluene, of order 5 micrograms per mil or so, as well as the fact that cesium carbonate is incredibly dense. It has a density of around 4 grams per mil. And as you see, both of those two features will provide will have impact on the mass transfer rates associated with the chemistries that we intend to run, and pose significant risk to scale up as we move across scales. The other comment that I'll make is the primary alcohol, this aryl alcohol here, is not actually soluble at room temperature, but is pretty readily soluble as the reaction temperature. So one of the other things that we want to keep in mind is the impact that heat transfer may also have on the system. We'll talk a little bit more about that in a few slides. I wanted to give a little bit of an overview or a snapshot of what the actual iControl interface looks like. So the panel on the left shows a typical recipe for a reaction. In fact, this is the recipe for the reaction that we're going to be describing here. Which involves simply, starting the agitation, heating up during a controlled heat up from room temperature to 70 degrees over an hour. There's a long extended hold followed by a cool down, a quench solution addition, as well as another solvent addition before the termination of the experiment. And one of the reasons why I kind of highlighted this particular protocol is that this particular protocol is written in a pretty easy graphical user interface kind of way. It's directly transferable from the EasyMax to the OptiMax. So it serves as a pretty robust means by which you can define the process recipe for a particular synthetic step. The other thing that I'm highlighting here is just a typical set of trends from this particular recipe that captures things such as the agitation speed here in pink. It captures the actual temperature profile, both of the reactor itself as well as the jacket services that are applied. It also keeps track of the amount of solvent, for example, that's been dosed in the quench and solvent addition steps. So this particular level of automation is very fruitful in the sense that it enables development or establishment of a very rich data set around a given experiment. It also enables unattended operation and enables us to work beyond what we would consider typical working hours by allowing the system to kind of operate and function in a self-sufficient way outside of working hours, weekends, evenings, etc. Again, this is really just kind of emphasizing the value of data maximization that can be attained through the use of automated lab reactors. So in addition to the rich data set that was highlighted on the previous slide that can be captured from within the iControl software, I'm also showing you here some of the data that can be captured using FTIR spectroscopy using an in situ FTIR probe. Again, the benefit of using FTIR is it can be used to profile compositional changes within the liquid phase of a particular reaction, and that's exactly what I'm showing you here. In this particular figure, I'm showing you in purple the actual profile of that aryl halide substrate as well as the primary alcohol that's present in the system in green as well. Again, one thing to note with that primary alcohol, it's not actually soluble at room temperature, so there's very low level of composition at the beginning of the reaction. But again, as you heat up, you start to dissolve additional quantities of that primary alcohol until you get to the point where it is fully or mostly solubilized, and that tends to initiate the reaction. Once the reaction kind of initiates, you start to see a consumption of both aryl halide and the primary alcohol, as well as formation of the desired product as well. One other comment that I'll make is this is a moderately complex FTIR spectra. To analyze the actual transformations that you're doing are relatively minor from a spectroscopy perspective. But using some of the advanced algorithms that are built into the ICIR software, such as Concert Pro, we were able to pretty clearly identify the three primary components using those algorithms and build a pretty robust data set pretty quickly. So that gave an example of a typical reaction profile. As we think about transitioning from scales, whether it be from the 100 ml to the 1 liter scale, or more importantly from the 1 liter to the 1,000 liter scale, one of the things that's very important is to think about the relevant rates that are active within a particular process. And I kind of break this into three kind of categories. You have mass transfer, heat transfer, and then reaction rates as well. So from the perspective of mass transfer, as I mentioned before, cesium carbonate is an inorganic base. It's sparingly soluble, but it's believed that there needs to be some degree of cesium carbonate within solution in order to facilitate the reaction. So from a mass transfer perspective, dissolution rate of the cesium carbonate is expected to be impactful. And not only is it expected to be impactful, it's believed to be sensitive to the KLA, or the dissolution rate, for this particular system, especially as you move across the temperature range, since you really don't see an appreciable boost in solubility as you move across temperatures. So obviously KLA is something that we want to keep an eye on. Additionally, cesium carbonate, as I mentioned, is incredibly dense, so its significant density poses challenges associated with solid suspension. In order to effectively dissolve material, you do have to expose that solid phase to liquid. So it's critical that you adequately suspend this particular material. So it's something that we want to make sure that we're understanding as we move across scales. Additionally, as I mentioned, the primary alcohol is not soluble at room temperature, so the dissolution rate has the potential to be impacted by things such as agitation rate, as in the case of the cesium carbonate. But as I mentioned, for that particular compound, as you increase the temperature, it readily dissolves. So you no longer have to be concerned with mass transfer as you move across temperature. From a heat transfer perspective, the reaction itself is mildly exothermic. But it's pretty well tolerated. It's expected to be pretty well tolerated as we move across scales, so there's no significant concern there. The other thing that I'll say is the temperature ramp that we were intending to impose, about 50 degrees over the course of an hour, is confirmed to be well within the equipment capabilities of the vessels that we were considering. So we weren't expecting any issues with being able to replicate that at scale. But it's obviously a critical step, or a key step, in making sure that the equipment you intend to operate at scale is capable of performing the experiment that you intend, or performing the reaction that you intend, in an analogous fashion to what you execute at small scale. So things like temperature ramps become critical in at least for investigation. Lastly, I'll talk about relative reaction rates. So specifically, the chemical reaction rates, are largely believed to be scale independent. So that's not something we necessarily need to be concerned with them as we move across scales. But at the same time, the interplay between these three different types of rates, mass transfer, heat transfer, and reaction rates, does and can and does manifest itself as varying relative reaction rates. So I think it's important for us to take steps as we move from lab to pilot scale to better understand the interplay between these various rates, and that's some of the things we'll talk about over the next couple of slides. So one of the things that we executed in order to better understand the impact that mass transfer has on the system is we looked at the impact that particle size of the cesium carbonate has on the reaction performance. As I mentioned previously, you have a mass transfer being dictated by a combination of your ability to suspend cesium carbonate as well as the solubility or the rate of dissolution of that cesium carbonate. So one of the things that we were looking at is whether or not changing the amount of the relative particle size of the cesium carbonate material, whether or not that had an impact on the observed reaction rate of this particular system. So on the top figure, I'm actually showing the reaction profile. It's the same reaction profile I shared on a previous screen, which essentially shows that over the course of about 2 hours from the start of the experiment, the reaction kind of proceeds through its full course. So you actually meet your conversion specification at about the 2-hour mark. In this particular case, we're using a typical reaction conditions using unmilled cesium carbonate that is as received from the vendor. This particular cesium carbonate has a specific surface area of 0.36 meters squared per gram. Now, if we repeat that experiment using virtually identical conditions, with the exception of using pin-milled cesium carbonate, what we see is that the reaction occurs quite a bit faster. Now, again, the difference here is that we're using cesium carbonate that has a higher specific surface area, just under double the specific surface area of the unmilled cesium carbonate. And what you can see is that instead of taking a full 2 hours to reach conversion, as we saw above, you're actually complete at about the hour and 15 minutes range. So this set of experiments is actually incredibly informative for us in the sense that the comparison of the milled and the unmilled cesium carbonate results in different observed reaction rates or different rate of conversion. And hence that it kind of indicates that mass transfer rate is indeed significant as we anticipated. We can't say that it is exclusively due to mass transfer from this set of experiments alone. However, it does say that mass transfer is certainly significant, and it's something that we need to manage as we move this process across scales and equipment types. So in order to facilitate the understanding of the impact that the particle size, for example, has and associated mass transfer has as we move across scales, we did a number of different things. One of the things that we did some process modeling to confirm that we were adequately suspending the cesium carbonate in the various reactors that we used. So this happens to be a screenshot from a Dynochem tool that's used to do a just suspended calculation, which essentially tells you the speed at which you would need to spin the impeller in order to ensure that the agitation that the solids are off of the bottom of the vessel, that they're at least suspended off of the vessel. So in this particular screen, I'm showing two different reactors, one EasyMax and one OptiMax, where you have the relevant geometrical considerations are input into the tool, the impeller geometry, and then the vessel geometry. And then the same thing is also replicated for the OptiMax and the EasyMax, or the OptiMax as well. So once you've actually input the relevant geometric parameters as well as some solution phase parameters, you're able to execute an NJs calculation. And what I'm showing here is a summary from that in silico simulation. So specifically, I'm looking at the EasyMax reactor, this first line here. What this tells us is that the simulation would predict that the scale we were operating in, the vessel fill, the solution type, the geometry, etc., you would need to be running about 620 or so RPMs in order to ensure that the solids are suspended. Now, there's some inaccuracy associated with this model, the correlation that's used in this model. That's partly due to an inability to readily ascertain S numbers for the particular impeller and vessel geometry, as well as just some deficiencies in the correlation itself. However, we generally find that this particular correlation is accurate, plus or minus 20% or so. So within that 600 plus or minus 20%, is likely where that just suspended speed should reside. At lab scale, we typically operate this at the 750 RPM settings, and in the prediction, the model prediction says that the solids would be suspended. Now, one of the nice things about an EasyMax reactor is you're able to see into the reactor, so we can visually confirm that this is indeed the case. And we did confirm that about 600 or so RPMs is right around the speed that you would need in order to adequately suspend that heavy cesium carbonate. We performed a similar experiment with similar simulation with the OptiMax reactor, seeing that you would need about 600 RPMs in order to suspend the material. This is in the probably suspended region as predicted by DynoChem, because we're running slightly below the NJs, but at the same time it's within that plus or minus 20% that I mentioned previously. Lastly, we executed this same simulation for a number of different reactors that we were considering for execution within our pilot plants here on site. We had the luxury of being able to choose a number of different reactor types. We specifically chose one reactor that was, let's say, better suited in order to suspend the cesium carbonate. And what you can see that if you run at the maximum RPM allowed in this particular vessel, 140 RPMs, you're sufficiently above the DynoChem predicted NJS. So we had a pretty high level of confidence that we were going to be able to adequately suspend the cesium carbonate, and therefore expected that the reaction would perform in a comparable manner as we observed at lab scale. Now, as a further mitigation, we did use pin-milled material prior to the first batch, so we did actually use pin-milled material to try and speed that reaction along as best we could to mitigate any risk associated with suspension as well as dissolution rate. In the second batch, we used a blend of pin-milled and unmilled material, and by the third batch that we were executing, we actually used exclusively unmilled material, and each of the three were successfully demonstrated. Appropriate conversion consistent with our expectations at lab scale. So again, one of the complications of this particular process is it's hot toluene, 70-degree toluene. So there's some IH concerns associated with hot sampling, so we don't actually have a full offline HPLC analysis. Additionally, complexities associated with the recycle of that hot stream coupled to that thick slurry that cesium carbonate induces prohibited online analysis using FTIR. So we don't actually, unfortunately, have a full reaction profile. However, at the end of the reaction, as dictated or as analyzed by HPLC, we indicated that the coupling reaction had gone to greater than 99% conversion in under 3 hours, which is consistent with all of the lab scale experience that we had to that point. So that was an overview of one particular reaction where we had some mass transfer limitations, and we used some tools such as the automated lab reactors coupled to some process modeling in order to identify and mitigate risk as we move across scale. What I want to highlight here is a second synthetic scheme, or a second reaction for the same process, where we were, instead of evaluating risk associated with scale-up, we were trying to identify the optimal conditions to execute the particular reaction. So the subsequent step in that chemistry is actually deprotection of the aryl ether that we described previously using aqueous sodium hydroxide. So another part of that particular molecule is protected with T-butyl alcohol, or with a T-butyl group. So we use sodium hydroxide to do a deprotection, resulting in this carboxylic acid, which the free acid is the final product of this particular synthesis. One of the things that we observed during our laboratory investigations is that elevated temperature and or significant excess of base were known to create colored bodies. And at the time, we were uncertain of how well those would be rejected downstream. So what we did is we actually performed a quick kinetic study to identify some of the preferred operating conditions, this being on a very abbreviated timeline, about 4 days. Now, this is not a fully rigorous kinetic mechanistic model or mechanistic understanding of all of the, for example, impurities that may be generated in this system, but rather this gives us an idea of approximately how long we should be operating as we, or how long we should be expecting this particular reaction to operate under a variety of set of conditions, which helps us to rapidly arrive at, let's say, somewhat optimal reagent stoichiometries in order to permit execution at pilot scale. Again, this was a very abbreviated timeline, 4 days from initial investigations until when material needed to be charged into the reactor at pilot scale. So as in the last particular case, the component identification for this particular system is quite challenging. You're actually looking at a pretty subtle spectral shift. We did need to employ, again, Concert Pro in order to identify the components of interest. In order to do this, we actually ran a reaction that is maybe atypical of our typical operating conditions, but was selected in such a way that it was to maximize the information density of the particular experiment. So we ran at a higher sodium hydroxide load, for example, and we actually induced a programmed temperature ramp versus an isothermal reaction to better estimate the impact that temperature has on performance of the reaction. As I mentioned, Concert Pro is necessary in order to pick out, key spectral features. In this particular case, we also needed to use referee data, reference trends based on offline HPLC to further aid in Concert's identification of components. So what I'm showing you here on this particular slide is both the aryl ether in blue, the free acid in red, the starting material and product of the deprotection, as well as some offline HPLC trending data. They're not on the same scale, but I just wanted to show that the use of referee data greatly improved our ability to actually monitor this particular reaction, and Concert Pro was critical in employing that data. So once we had successfully identified the components using Concert Pro, we were able to take that FTIR data and pull it into DynoChem, where we generated a model using a base-catalyzed ester hydrolysis mechanism and then regressed the relevant kinetic parameters against that FTIR data. So the model that I'm showing you here is highlighted by the solid lines. That's the DynoChem model prediction for both the free acid as well as the aryl ether. And the dotted lines is a subset of the FTIR spectra here. So you actually see pretty reasonable agreement between the model prediction as well as the FTIR data that's generated. So using this particular model, we were able to simulate a number of reaction scenarios, and from those reaction scenarios, we identified that a 2.5 equivalents of sodium hydroxide in a reaction temperature of 30 degrees would result in a reaction time of 21 hours. We felt that this was a suitable balance between, a rapid reaction or moderately rapid reaction, balanced against the elevated temperature and base, which were known to create undesirable colored bodied impurities. Once we actually executed this, once we executed this simulation, we then did a lab scale experimentation where we subsequently confirmed these conditions were complete in 23 hours, and those served as the basis for the pilot plant execution that followed. So with a firm understanding of the optimal operating conditions that were determined at lab scale, we subsequently used those same conditions, so 30 degrees C and 2.5 equivalents of sodium hydroxide during the earliest batches at pilot scale. And we demonstrated greater than 99% conversion at the 24-hour time point, which is well aligned to the predictions of the DynoChem model as well as the lab scale experiments that have been performed. So this is actually, again, another example where some use of automated tools, automated lab reactors, coupled to the process analytical technologies, FTIR for example, really enabled us to pretty rapidly understand exactly the optimal conditions in order to run a successful pilot scale campaign. So at this point, I just want to kind of conclude by making a couple key statements around specifically the fact that in process development, program timelines frequently dictate having to make critical decisions around, for example, the equipment selection, as well as the manner in which you're going to execute the process or process design decisions. They need to be made, and oftentimes with pretty minimal process understanding. As I mentioned previously, we've demonstrated that the use of those automated lab reactors automated reactors coupled with online PAT tools, for example, enables pretty rapid decision making, which has enabled us to sufficiently identify and mitigate risk as we move across scales. Furthermore, although we didn't really discuss it much here, this particular work has the potential to go on and become the foundation of more detailed process understanding build as we move the program forward. Obviously, that has to be commensurate with the program's probability of success. In this particular case, the program was terminated shortly after our initial pilot scale activities. But had it moved forward, the data that was gathered here, as well as the methods that were employed to gather that data, would have continued to enable efficient development of our process understanding in that program. With that, I'd like to just offer the following acknowledgements, and thank you very much for your attention.